Hey everyone, and welcome. Ever look up at a massive bridge or a skyscraper and just wonder how it all stays up? Well, it's not just steel and concrete. It's a whole set of fundamental principles. And today, we're diving into one of the most important distinctions in all of structural engineering, the difference between what we call determinate and indeterminate structures. So let's kick things off with a little puzzle. On the screen, we've got two beams. And, at first glance, they look pretty much the same. They're both just simple beams with supports on either end. But for an engineer, these two things are worlds apart. So here's the puzzle. Beam A, with its one pin and one roller support, is super straightforward. I mean, a first-year engineering student could figure out the forces on this thing with just some basic math. But beam B, with two pin supports? Oh, that one's much, much trickier. So what's the big secret? What is it that makes one so simple and the other so complex? Well, it all comes down to a concept called equilibrium.
To crack this puzzle, we really need to get a handle on the absolute bedrock of structural analysis, equilibrium. All it really means is that for any structure to be stable, to not fall over or fly away, all the forces and all the twisting effects acting on it have to perfectly cancel each other out.
For any 2D structure, that whole balancing act is captured by these three really elegant equations. The sum of all the forces going side to side has to be zero. The sum of all the forces going up and down has to be zero, and the sum of all the moments, or the rotational forces, around any point also has to be zero. That's it. For basic analysis, these three equations are the only tools in the toolbox.
And that leads us right into our first big definition. A statically determinate structure is one where the number of things we don't know, like the forces at the supports, is exactly equal to the number of equations we have to solve them. In 2D, that means we've got three equations to find three unknowns. It's a perfect match. These are the simple structures.
But then you've got the other side of the coin, a statically indeterminate structure. This is one where you have more unknowns than you have equations. It might have some extra supports or members that aren't technically needed just to keep it stable. These redundant parts mean our three little equations just aren't enough anymore. We literally have more questions than answers, and that's exactly why these structures are the tricky ones.
So, you might be wondering, how can we tell them apart without getting bogged down in a bunch of physics? Well, luckily for us, there's a pretty simple formula we can use. It's kind of like a litmus test that turns this whole abstract idea into a simple counting game. For a typical frame structure, the process is dead simple. First, you just count up the number of members. We'll call that M. Next, you count the support reactions, R. Those are the forces from the ground pushing back up. And finally, you count the joints, J, which is just where all the members connect. Then you just plug them into this comparison. Is 3M plus R greater than, less than, or equal to 3J?
So what does this little comparison actually tell us? Well, there are three possibilities. If the left side is less than the right, the structure is unstable. It's basically going to fall apart. If they're exactly equal, bam, the structure is statically determinate. And if the left side is greater than the right, you've got a statically indeterminate structure. Let's actually put this to the test.
Okay, let's try a real example. Here's a simple frame. Let's count it out. We've got three members, three support reactions from the ground, and four joints where they meet. So we plug that in. On the left side, we get 3 times 3 plus 3, which is 12. On the right, we have 3 times 4 joints, which is also 12. And what do you know? 12 equals 12. They're perfectly balanced. This frame is officially statically determinate.
All right, now let's check out an indeterminate example. This beam has 3 members, 6 support reactions, and 4 joints. So let's run the numbers. 3 times 3 plus 6 gives us 15. On the other side, 3 times 4 gives us 12. Well, 15 is definitely greater than 12, so the scales have tipped. We know for sure this beam is statically indeterminate.
And hey, that difference, the gap between 15 and 12, that's not just a random number. That difference of 3 actually tells us how indeterminate the structure is. In this case, we'd say it's indeterminate to the third degree. That means it has 3 extra or redundant forces that make it so tough to analyze with just the basic methods.
Okay, so this all brings up a really big question, right? If these indeterminate structures are so much harder to figure out, why on earth do we use them all the time? Why would we build things the complicated way when a simpler option exists? Well, the answer comes down to two big things: safety and efficiency. This quote right here just nails it. Those extra supports, those redundant members, they create multiple load paths. Think of it like driving with a GPS. If your main route has a traffic jam, the GPS finds you another way to go. It's the same idea in a structure. If one piece fails, the load can just find another path to the ground, which prevents a sudden catastrophic collapse.
And the perks don't stop there. Because the loads get shared more effectively, indeterminate structures can often be built with less material, which saves money. They also tend to be a lot stiffer, which cuts down on vibrations and just makes them feel more solid. All of this gives architects and engineers incredible flexibility to design wild new forms and create buildings with huge open spaces.
So what this all boils down to is that every single time an engineer or an architect starts a new project, they're facing this fundamental trade-off. It's really a choice between two totally different ways of thinking about design.
On one side, you have determinate structures. Yeah, they're simple to analyze, but they have a major weak spot. Since there's only one path for a load to travel, if a single important piece fails, the whole thing can come down. But on the other side, you've got indeterminate structures. Way more complex to analyze for sure, but they are so much more resilient. Those multiple load paths give you that critical safety net, and they let you build more efficient, more elegant things. It's the classic showdown, simplicity versus resilience.
And that brings us to one last thing to chew on. The very complexity that used to make indeterminate structures a nightmare to analyze, well, our computers can solve those problems in seconds now. So in this age of incredible computing power, is the simple elegance of a determinate design even relevant anymore? Or has the incredible safety and efficiency of redundancy made it the clear winner for modern engineering? It's definitely something to think about the next time you're driving over a bridge.